All right. I've been in this job for over a year now, and basically one of the ideas coming in was to shape a research agenda. What are the major themes that we wanted to sort of focus our bets on, right? Because previously, I think the way things had worked was Mcity had research dollars and just sort of funded a lot of different projects. And the idea was, for me to shape a research agenda and focus in specific areas, right? And so these are the three major trends that I've been working on. Let me see where this laser pointer. There we go. So these three trends here, and then the sub bullets or the projects that we're running on each. So the first one is about digitization, right? The world is becoming much more digital, and communication networks are getting dramatically lower latency, higher bandwidth, right? So that really gives us the ability to demonstrate what we did yesterday with Mcity 2.0, where we have distributed mixed reality testing. We're not going to discuss that today because we hit it very hard yesterday. So we don't need to go over that topic again, but that's a major trend. Artificial intelligence clearly is an enormous trend, right? The first sort of artificial intelligence conferences were in the 1950s, right? And that's when the original perceptrons were developed. And that was 75 years ago, right? And so like for 60 years, AI just sort of went sideways like this, right? And, a little bit of hype and then the bubble bursts and, no sort of real significant upward progress. And then within the last sort of 15 years, probably sort of kicked off in my mind by, like ImageNet and AlexNet's performance on that, which sort of galvanized in, everybody's attention in the space, you know, data accessibility, because everything's digitized now, and compute power with the GPUs that are available have just driven this massive inflection point where, for sort of 60 years, almost nothing happened. And then in the last 15 years, it started to build. And if you look in the last 2 years, the model sizes and the training data sets have increased by an order of magnitude each year. So we're just absolutely on a very steep exponential in artificial intelligence right now. We're running two projects. One is the data engine and the other is AI safety. The data engine's fundamentally about how do you create and improve AI networks. And then AI safety is about fundamentally the fact that these are black box models. So, at the root of it, we got to admit that we don't know what's happening inside those models, right? They're working, we test them, they seem to work, but sometimes they don't, right? So how do we work in a safety critical environment like we do in mobility, with black box models? And then the third major trend is this infrastructure assisted autonomy, because the autonomy that's on the road today, like from Waymo, is effectively autonomous autonomy, right? It's the vehicle has all its own sensors, all its own compute, it's making all its own decision making on board. But there's a trend here driven by smart infrastructure where sensors are getting installed into the world, into smart intersections, into smart buildings, and compute is going along with those sensors, right? The infrastructure is getting smarter. So how can we have infrastructure sensing and compute interacting with, mobility sensing and compute to be synergistic and to work together to make something better? And that's really what we're looking at in depot autonomy, which I'll take you through. So first off, we're going to go through the data engine. So, you know, it always starts out simple, right? Somebody says, I found a pain point that I want to solve by creating, an AI network, right? So I get some data and I train a model. And as soon as you do that, you figure out that your model doesn't work in a bunch of cases, and your training data set wasn't diverse enough, and you didn't curate your data set well enough. And so there's some bad data in there. And there's all these things. And so you sort of build out this complicated ad hoc process where you add a tool here and a tool there, and the pipelines become messy, right? And so what we're trying to do here at Mcity is say, it doesn't have to be messy, right? It can be better structured if we think about what a data engine is, right? So here we have the model we want to create, this AI algorithm. Maybe I should, for the people online, point with this. So, oops, that's the downside. Then slide advance. Our AI algorithm is the thing we want to create, right? And we get a training data set, we use that to train the model. But then we just need to evaluate the model with things like Mcity 2.0 or full simulation. Then we deploy it into the real world. We see how it works. We find issues. We bring those back. We auto label them. We add them to the training data set, retrain the model, reevaluate it, redeploy it, find and fix issues, and we just continuously run, this loop to make the models better and better. And why, what's the hoped for goal, right, is to develop, a trend like this, where if you have model accuracy on the y-axis versus data set size on the x, right? This model, we just want it to be getting better and better at over time, more and more accurate as we train it on more and more data. And the data is getting not only larger, but also better curated. Think of data curation like, weeding and pruning in the yard, right? It's going in and finding the bad stuff and getting rid of it from your data set. So that's the dynamic we want to see. There's two models here that I want to sort of introduce as a concept here. This idea of knowledge distillation from a large teacher model to a smaller student model. So the teacher model is a big model that can only run on a data center, right? It's a very complicated, large, very accurate model. And the student model is the thing that you actually deploy at the edge, right? So the student model is the thing that goes in your car or goes into a traffic signal controller at an intersection. So this needs to be efficient, right? And it's probably never going to be as good as the teacher model because it's just not as big, right? But if we train it on larger and larger amounts of data that's well curated, we can make it approach what the teacher model can do. And the way we specifically do this is we train this teacher model as an auto annotator of the data sets that then train the student model. So that's how we get to large data sets quickly, is because instead of having to have thousands of human annotators drawing bounding boxes on images, right? What we do is we train a large teacher model to do that auto annotation, and then it can process a lot of images very efficiently. And then we can use that large number of images to train this smaller student model that's deployable in the real world. And what we find is that, at some point it plateaus, right? The teacher model has taught the student all that it can handle, right? And so performance plateaus. And so then you got to upgrade your teacher model, right? So you get new data, you teach your teacher model new things, and then you use it to annotate data sets, and that then trains the student model, right? And the student model moves up the curve. And so, this is how you run a data engine efficiently to get this, ever increasing capability in your student model. And so then here's the actual thing we're building, right? I showed you the other slide that was very sort of simple. And the reality is, things are always more complicated, but there's a structure to this pipeline that I'll take you through because we're going to build this up bit by bit. But the major structure is this is where we train the student model in this loop, and this is where we train the teacher model in this loop. And this loop here is a simulation loop where we use simulation to improve the quality of the model. So let's just step through this bit by bit to sort of make it more easily digestible. We'll take it one bite at a time. So you start with a raw data set. So in our case, the main raw data set we have access to that's large volume is from the Smart Infrastructure project, where we have the fisheye camera data streaming to an S3 bucket in our AWS cloud, just collecting continuous data from intersections. But this could also be a raw data set like a vehicle, if you have vehicles with sensors on them, collecting that kind of sensor data. And the first thing we do is we go through this large data to try and find the interesting images, right? So you can't just process all the data, it's too much. And that wouldn't even be helpful because a lot of it would be repetitive. So you got to go through the data and curate it and find the interesting pieces of data within that. And then the first thing to do is to train your teacher model. And for that, we use human annotation. And the reason for that is the teacher model is sort of the ground truth for teaching the student model. So we really got to make sure that the teacher model is trained on well-annotated data. And so still the most trusted source for that is human annotation. But it's not a lot of data, right? It's a smaller amount of data that we send to the humans to annotate than what was done previously. And this human annotation effort creates the teacher training data set, which we use to fine-tune a large model. So there's lots of large models that other bigger groups have trained and they've put out on repositories like Hugging Face. And so we can go there, we can take their models, like for instance, the one we use right now is called Codetter. So others created that large model, and then we use our data set to fine tune that large model to work for our use case. So we can reuse work that others have done in that way. And then we test it to see how well it works. So when the humans do this annotation of data, we put 70% of it into a training data set, and then we hold out 30% that the network doesn't get trained on. And that's our testing data set, where we make sure that in that curve that I showed on the last slide, that we have this, improvement and not degradation of model accuracy. And then once we've got the model to where we want it, this large offline model that only runs on our cluster, then we can use it to auto-annotate. So this is a much bigger stream of data than this. So now that we've got a model to annotate our data, we can pump a lot more data through it. And then we use that to build a larger student training data set, which we're going to then use to train our student model. And this is the small model that's deployable on the edge devices. And then you need to test that. So you take the same evaluation data set we had down here, and you test it doing regression testing to make sure that the retraining you did is improving the model. And then we get into the simulation loop where we can take the network we've developed here and put it into its system environment, whether that's a traffic environment or on a vehicle in a deployment like that. We can do closed loop testing in full simulation with that. And where we find issues, then we can use that simulation data to create synthetic data, and we can actually add the synthetic data back to our student training data set to improve our training data set, to retrain our model, so that when we get back to this place, we've closed those issues that we found in simulation. And then, when we want to do some more specific testing on specific risky and rare scenarios, we can use our Mcity 2.0 capability, our mixed reality testing at the track and in the digital twin. And then comes the deployment phase. Right now, our deployment sites are the traffic controllers at intersections. So loading the Mcity algorithms so that they're running. I should have said that here. The infrastructure camera algorithms that we're creating for object detection and tracking, we call Mcity. But those also they start from a pre-trained model that's called YOLO V8, which we then tune for our use. And then we can deploy it out to the traffic signal boxes that are controlling the intersections. And then you can have some triggering. We get all the data back, but you can do some triggering to find interesting events in that data stream, and then triage them to say, okay, here's a place where our algorithms are not working well. So let's get more data so we can do this retraining loop. So you find the issues, you set your triggers to find similar data that's in your large S3 bucket that's in the cloud. You pull that stream in, do the auto annotation, retrain. So you run this student loop more frequently and the teacher training loop less frequently. Mostly the teacher training loop only gets kicked off when you find that your student model is sort of plateauing with more data. So, Amazon AWS has been critical for us. It's where we store all the data and use some of their curation tools. We're also really just getting started, but using Voxel 51 for data curation. It's open source, so anybody can use it without charge. The repository where we get the large models for doing the teacher training and fine tuning is the Hugging Face repository. We have our own cluster of compute it's called Lighthouse, but it's dedicated for our use at Mcity for doing all our training and simulation and model inferencing. We talked yesterday about, integrating the NVIDIA high fidelity sensor models. So that is definitely something we are very interested in getting started with. Some real opportunity there. Parasim is obviously important in this stress testing of the models. So Parasim creates the adversarial driving environment. And excuse me, my kids have gotten me sick. I have two kids who are freshmen at U of M now, and they've both been sick since day one of classes. So every time I see them on the weekends at a tailgate or something, I get reinfected. Mcity 2.0 is an area where we can use that to do more evaluation of how well our models work. And the Smart Intersection project is our current data source. I am looking for a fleet data source. I don't have one yet. That is something I want to develop. So, we've done work on all aspects of the data engine. The areas that, I would really like to improve going forward is doing more work on, getting a fleet data source stood up, as well as, all the work that we discussed yesterday in our announcement with MITRE and NVIDIA is really going to sort of jumpstart all the work we're doing here on the computer simulation side of stress testing the AI networks. So that's the data engine. Next topic. How am I doing on time? I've forgotten when. 10 more minutes. Okay, AI safety, I'm going to give a little short shrift to because I want to spend more time on depot autonomy. So we talked about this, very extensively at the Congress. So I'm not going to go over this slide again, but the central question is, you've got these black box AI models, they're being used in safety critical situations. How do we ensure AI safety? Henry has the paper in Nature that takes you through the curse of rarity, which says it gets really hard to just drive more and more miles to find more and more issues, because you got to get out to 100 million miles, which is out here at like 10 to the minus eighth, right? So the cost to do that, to find these really rare events, just goes up very significantly. So what we're looking into at Mcity is creating a multi-layer defense, the sort of referred to as the Swiss cheese model, because the idea is, if you've got 4 layers of Swiss cheese here, right, if they're different layers of defense, right, you can stop different failure modes by having multi-layers. So this is our sort of multi-layer defense here on the left side. Approach one is what everybody's doing, is just to try and find more edge cases and train their models. This one is looking at models are good when they're interpolating within their test data, they're bad when they're extrapolating. So how can we make sure that we know when they're extrapolating and we take countermeasures? These are alignment techniques like reinforcement learning by AI feedback, where you set a set of rules and then you use reinforcement learning to make the model live by those guardrails. Rules like always stop at a stop sign and always stop at red lights and yield to pedestrians and crosswalks, things like that. These provably safe algorithms are the ones that are more deterministic that we're used to. They're things like control barrier functions to make sure vehicles don't bump into each other. But these are not black box, right? These are human-coded C++ algorithms. And then approach 5 is the most interesting one. Henry referred to it somewhat in the DARPA project, but using these foundation models that are more general intelligence to try and go after trying to figure out how to make AI driver models generalize like humans do, right? If my teenagers see a certain situation just a handful of times, they know how to handle it, versus an AI network, you got to show it like a million examples, before it figures it out, right? Because they just don't generalize like we do as humans. So how do we figure out how to make AI models learn to learn and not just be pure imitators? All right, with that, depot autonomy. So this is in the infrastructure assisted, infrastructure enabled autonomy, where smart infrastructure investment is happening. How can we use it to do better autonomy? And the use case I'm looking at is within a depot. Think like an Amazon fulfillment center. So within that constrained operational design domain, a depot with a fence line around it, everybody inside it's an employee, everybody knows and is trained. But within that constrained operational design domain, how could we take vehicles that have just normal cameras and radars, like happen for level 2 driver assistance features, and make them autonomous L4 AV capable by adding infrastructure perception and routing? So how do you take the existing sensors that are on existing vehicles and the sensors that are in the infrastructure and use some smart algorithms to get them to work together so that they can actually autonomously marshal vehicles through the space? And this, we've shown this video a number of times, but here's Mcity, our pitch that we're going to make to NSF for funding is to expand the footprint of Mcity into building an actual depot space here, connected to Mcity on this side and connected out to Green Road on that side. And I'm going to skip the video in the interest of time here. But what we've been doing really intensively, I've spent a lot of time on this, is assembling the coalition of the willing here. And I really am focused on not only doing technical feasibility, which is what we're all used to, the engineering task, but also looking at the business opportunity, because great engineering ideas never see the light of day unless there's a solid business case. So, figuring out the business opportunity is critical, as well as documenting engineering requirements. Because, when I was at Ford and people in academia did research and just sort of made a white paper or something, that was not really what I needed. What I needed was the specifications. How do you build something like this? What requirements does it need to meet? How are you ensuring safety? How are you testing it? What are the performance metrics you're testing it to, right? Documentation of the systems engineering is critical for that. So the folks we've got working on this, since January, we have Katie Skinner and Ram Vasudevan from robotics, with a team of students working on the perception and planning stack. We have just signed on Nobilis to do the orchestration part of it. So think of that as like the air traffic control system of the depot. And Nobilis has created a really interesting state-of-the-art way to do that that's decentralized, which is really interesting, which is why we've signed them up to do that work. Aline Eid is doing precision localization. It's part of our safety case. So trying to figure out where all the humans are in the environment and robustly tracking them, because the number one failure mode we need to avoid is having our autonomous vehicles hitting workers in the fulfillment center. Communication networks is critical as well, right? If you've got vehicles driving around and infrastructure sensing and routing, there needs to be robust communication between the two. And Professor Shinsha from University of Dearborn is going to work with us on that. He recently came from UCLA, where he worked on the Open CDA standard. And so he's going to be helping us with the communication networks part of depot autonomy. And there's a startup called NIFT, which is creating our test platform. They're actually creating it for the students in Tech Lab. It'll be a Tech Lab project in winter term. But this would be like, the electric skateboard chassis kind of the thing that would be autonomously marshaled through the depot. But it'll be a completely open source platform. So the students will be able to completely control, reprogram it any way needed. On the business side, Peter Adrians has done a lot of work on infrastructure finance. And so he and a MBA student who he's advising are helping us with the business case, as well as we have a Ross team of 4 MBAs that are working on the business case as well, and the market sizing, like what's the market potential for depot autonomy. On engineering requirements, we have Gaurav Pandey from Texas A&M, who's doing the concept level work. And then we have student teams under Professor Boardley, who are doing the systems engineering work as capstone projects in their coursework. And then CAMP, the consortium that's run by GM and Ford, is working with us on developing an SAE standard to sort of codify how to make the system interoperable for vehicles and infrastructure that would then be published in an SAE standard. So that's our team that we got working on it. Schools that we're touching within U of M right now, the ones at the top here in bold are ones that we're actively engaged with right now. With my focus, being to try and make these as multidisciplinary as possible. And these are the ones we're reaching out to right now. School of Information, both on some of the data science topics as well as some of the human machine interface topics. Aerospace engineering, because we'd like the depot to be multimodal, to have, drones coming in and out as well as delivery vans. Architecture school, because we'd like to make the depot a software-defined building, right? We don't want to just make it a dumb brick and mortar, right? We want to make this a modular, updatable, fully connected building of the future that can be updated by software. Law school and public policy, I've added more recently, actually, because, it's just, there's an article in the Wall Street Journal I saw just this morning that the headline of it is something like, that the dock workers are protesting automation in shipping yards, and so there's a real, larger societal context for how does automating these things, affect the people who were doing those jobs, right? The companies say, well, we can handle more freight, so we'll get more business, so we'll need more workers. But what the workers see is that it used to take 30 people to do a job that's now being done by 4, right? And so sort of balancing that and having that larger discussion, which is great for us at Mcity because we're not really going to make depot autonomy. We're not capitalists in that sense, right? We are researchers looking at this as, and so we can take on the hard questions, right? So that's one of our advantages. Industry partners. So we're always looking for industry partnership, right? Obviously, depot operators would be sort of my number one group that I'm looking to recruit. Smart buildings, I think this is a really interesting space. Network providers, obviously the communication networks are critical. The vehicle platforms, so, OEMs that would have vehicles that would need to interface within a depot environment, as well as tier 1 suppliers who are actually developing some of these systems already. So opportunities to get involved for those that are interested. Our goal is, as Henry said, is to get a large NSF funded project, $20 million to do this work. Okay, made it. Questions?
Presentation, Greg. There's so many issues we'd like to talk to you about in your presentation, but so many parallel to the things we're doing. But just a couple comments on the depot work. Have you considered reaching out to the DoD, Logistics Management Material Command, because they have a strong need for for supply management? Their depots are very chaotic typically. The toilet paper doesn't end up on the same place, when they're mobilizing troops. So some sort of smart autonomous material management in depots that they have to set up on the fly. It's an excellent application for the
yeah. I would love to utilize your network to do that. Noblesse has indicated that they have some of those connections, but you know how the connections go, right? It's always good to have multiple networks to work through. So yeah, I'd love to talk to you about that. DoD is obviously very attractive to work with, so we would love that.
And just another follow-up is we've been tracking the longshoremen strike on the West Coast and the East Coast too, doing a lot of analysis of the economic impacts of that too. We have an economic modeling framework called MUST that could be another thing. We could
Yeah, that's very interesting.
program into, guys asking the questions about what the implications and policy and labor management. So that might be a tool to help, play out some of the, impacts of,
Yeah.
of autonomy.
Right. Yeah, I think that would be awesome, because laying that out from a model is a nice way to do it. That's maybe we can sort of separate ourselves from the emotion of it, right? And just sort of lay it out as, this side is saying this side is saying this, we run the analysis and here's what we think, right? Yeah.